Today we're going to be talking about radicals.
Please remember that these are the parts of every radical expression. The first part is the radical symbol. The reason why this is called radical expression is because it is an expression that contains the radical symbol. Our A here is called the coefficient. The coefficient is a number multiplied to the radical expression. And the letter N here is called the index. This tells you which root you're looking for. Please remember that if the value of the index is not written in there, it means that that invisible number is 2. We also have a letter C, and this letter C is named as the radicand. A radicand is the value that you are taking the root of. So this expression that we have here is read as A times the nth root of C. Now let's look at some specific illustration on radical expressions. So this expression that we have here is read as 5 times square root of 7, where our 5 is the coefficient, the 2 is the index, and the 7 is the radicand. Now we remember that if the index is 2, we don't have to write it. It becomes invisible, so that we can go ahead and rewrite this as 5 times square root of 7. So these two are the same. The second expression that we have here is read as 4 times cube root of 5, where our 4 is the coefficient, 3 is the index, and 5 is the radicand. In this next example, we read this as the 4th root of 25. If you notice, there is no coefficient. We remember that if there's no coefficient in front of the radical expression, that invisible coefficient is 1. So there's number 1 right there. So we can go ahead and read this as 1 times the 4th root of 25. So that is how we read radical expressions.
First up, we're going to look at simplifying. We're going to have a few examples. So if I've got, let's do the square root of 75, and we are supposed to be simplifying it. Now, what you want to do is you want to think about what numbers you know that can multiply together to equal 75. And I know that 25 times 3 equals 75. So here, I'm looking for branches that stop. Okay, so this 3 won't go any further. Only 3 times 1 equals 3. So this is what they would refer to as a prime factor. Okay, so I'm going to underline it because when I get to the end of my factor tree, I want to know where all of my endpoints are. So it'll be easier to find it. 25 though can split into 5 and 5, and then 5 is done and 5 is done. So this is my factor tree for 75. What I'm looking for here when I'm simplifying a radical is first of all what the index is. When there's no number here, that means that the index is 2. We're taking a square root. So because my index is 2, I'm looking for groups of 2. This right here is a group of 2 5s. I have 2 5s here, so that is my group of 2. This 3 doesn't have a group to go with. There's not a match to it. Okay, so we're going to look at what we do with those. This group of 5 here, because I have 2 of them, that means I can take a 5 on the outside of my radical here. So these 2 5s become a 5 on the outside because I can make 2 of them. And then this 3 right here, since it doesn't have a match, it's going to stay on the inside of the radical. So then that tells us that the square root of 75 simplifies to 5 square root of 3. All right, let's look at the next example. So this time we're going to have a different index. We're going to have a 3 as our index. That means the cube root. So we're going to take the cube root of 54, and we need to simplify that. Okay, so before we started with our factor tree and just assumed that we knew 25 times 3 equals 75. But let's say maybe you're looking at 54 and you don't think of a number or two numbers that can multiply together. What you're going to do is you're actually going to use kind of one of the tricks that we've got. 54 is even. Because it's even, that means I can always divide it by 2. So I'm going to take this, and I know that 2 is going to be one of my numbers, and I want to figure out what that other number is. Maybe you already know it, but just in case you don't, let's look at what that is. I'm actually going to divide 54 by 2 to find out what this other number is. So 2 goes into 5 2 times. So then 2 times 2 gives me 4. 5 minus 4 is 1. This 4 will bring that 4 down. And then 2 goes into 14 7 times. So then 2 times 27 equals 54. All right, so now let's separate the 27. I know that 3 times 9 equals 27. That 3 is done. This 9 is 3 times 3. Okay, so now I have an index of 3. Before, I had an index of 2, and I was looking for groups of 2. Now that my index is 3, I'm looking for groups of 3. So here's a group of 3. 3 3s right there. So this means that a 3 can go to the outside of my radical. And then this 2 that does not have 2 other 2's to go with it is going to stay on the inside, which tells me that the cube root of 54 will simplify to 3 cube root of 2. All right, next one. I'm gonna do one more increase to the index. Now we're gonna look at the 4th root. So my index is 4 now. And we're gonna take the 4th root of 80 and we're gonna simplify it as much as we can. Okay, so again, we're looking at this number. Maybe we're noticing that it ends in a 0. That means you can divide it by 10 or you can divide it by 5. Let's do 10. So 10 times 8 would give me 80. You can split this into whatever numbers you know, so that would be fine. So 10 times 8 is what I wanted to do. 10 can be 5 and 2, so these are done. 8 can be 2 and 4. So be careful with this one. A lot of people make the mistake of making 8 4 and 4, but just remember we're doing multiplication, not addition, so it's 2 times 4. Oh, and actually the 4 is not done. 4 can split into 2 and 2. So here's all my endpoints. And just like before, right, my index tells me the number I need in my group. So I need a group of 4. So right here, I've got 4 2's, which means a 2 can go to the outside. And then this 5 right here does not have 3 other numbers that match it. So it is going to stay on the inside. So that means that the fourth root of 80 simplifies to 2 fourth root of 5. Look at a couple extra examples of some special circumstances that might come up. So let's say we're taking the cube root of 64. Cube root of 64. So I want to split 64 up. I'm going to do 4. I'm going to do 4. And then 64, I was going to divide that by 4. 4 goes into 6 one time. 1 times 4 is 4. 6 minus 4 gives me 2. This 4 will come down. And then 4 goes into 24 6 times. So this is 16. 16 can split into 4 and 4. Okay, so let's finish these. I've got 2 and 2 there, 2 and 2 here, and 2 and 2 here. So that's the finished factor tree. Okay. So I'm looking for groups of 3. So I have a group here with 3 2s and a group here with 3 2s. So this shows me that I have one of these here can be a 2 on the outside, and the other one of these here can be a 2 on the outside. So we can show where the different 2's are coming from. Okay, so now here I'm wanting to see what's left over, right? Because this is on the outside of the cube root and this is on the outside of the cube root. But if I look at my factor tree, I've taken everything away. I don't have anything left on the inside. So actually, this cube root can go away. So all that's left is these 2 on the outside, and I just need to multiply them together. So 2 times 2 gives me 4. So then the cube root of 64 simplifies to 4. All right, let's see another special example. Let's say I was going to take the square root of 14. So with the square root of 14, I know that this can separate into 7 times 2. So here, 7 and 2, those are both done. They won't go any further. So I don't have any groups of 2 that I'm looking for because my index is 2. So then nothing can go to the outside. Everything just stays on the inside. This 7 stays inside, this 2 stays inside, and they just multiply back together. So the square root of 14 is actually as simplified as it can be. All right, so this one would be the answer for itself. Let's look at one other example where maybe we've got a couple things on the outside and a couple things on the inside of one problem, okay? All right, let's say we've got the square root of 216 and we're wanting to break that factor tree up. I think what I would do would be to try 4. So 216 divided by 4. 4 goes into 21 5 times. 5 times 4 is 20. So 21 minus 20 is 1. I'll bring the 6 down. 4 goes into 16 4 times, so that gives me 54. 4 splits into 2 and 2, so both of those are done. 54 can split into 6 and 9. So the trick here that I would recognize is that I know that this number is divisible by 9 because 5 plus 4 equals 9. And then whatever number 9 needs to multiply to is just one more than whatever the tens place is. So 5 plus 1 gives me 6. So 6 times 9 equals 54. 6 can split into 2 and 3, so both of those are done. And then 9 splits into 3 and 3. Okay, so I have an index of 2. It's a square root, so I'm looking for groups of 2. So I have a group of 2 here. I have a group of 2 here. And then this 2 and this 3 are all alone. They don't have a match. So this 2 here can go to the outside. And then this 3 here can go to the outside. So then I've got 2 times 3 here, from here and here. And then this 2 doesn't have a match, so it's on the inside. And then this 3 doesn't have a match, so it stays on the inside. From here, I'm just going to multiply the outsides back together and multiply the insides back together. So 2 times 3 gives me 6, and 2 times 3 gives me 6. So the square root of 216 can simplify to 6 square root of 6. Eventually, you will start to recognize the factors that will give you the groups that the index tells you to look for. For square roots, these numbers are called perfect squares. And for cube roots, they're called perfect cubes.
For an example, let's look at the square root of 12. When we do a factor tree for 12, you can see that it splits into 4 times 3. The 4 is on the perfect squares list, so that could tell you that 2 is going to be on the outside without ever having to finish the whole factor tree.
So beginning to recognize these numbers can help you save time.
Radicals, radicals, I'm about to simplify these. 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 All these numbers ain't perfect. Some of them you gotta work it. Let me see if you can find the square that radicant. These numbers acting crazy. I don't know why they made me come at them with the lazy. Radicals, they never faze me. Take 24 example, 4 times 5. Yeah, I'm about to get it live. The square root of 4 is 2. Let me set it out front for you. And all that's left on the inside is the foregone factor that pi. To find these factors we strive. 4, 9, 16, 25. Radicals, radicals, I'm about to simplify these. 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 Let me confess that I'm doing my best to show you all the rest when it comes to this X. Call my boy Steven, I'll start reteaming. He said look out for them even. Stevens, let me tell you what I'm scheming. The reason is simple enough. Take half of it, yeah. Divided by 2, that's what's up. But what if it's odd? Oh my god.
Okay, when you are adding and subtracting radicals, you have to make sure that the index and the radicands match. So let's say we're looking at the square root of 50, and we're adding that to the square root of 15. So the first thing I want to do is check to make sure that the indices are matching, and they are. Both of these have an index of 2, so that's the first check. I know I can maybe add these together. The next thing I want to do is look at the radicands. First glance, this 50 and this 18 are not the same number. So I think maybe I might not be able to add them together. But what I want to do is see if simplifying them can make the radicands match. So if I do 50, that could be 5 and 10. So 5's done. 10 is 5 and 2. All right. Here I'm looking for groups of 2 because my index is 2. So I have this group of 2 5s. So a 5 can be on the outside of my radical. And then this 2 doesn't have a match, so it's going to stay on the inside. So that is simplifying the square root of 50. Let's look at now 18. So 18 can split into maybe 2 times 9. That could work. 9 can split into 3 and 3. So there's my group of 2 3s here. And then this radical here has a 2 in it because the 2 is what's left over in this factor tree. So now these radicands do actually match. So I have an index for both of them is 2, and the radicand on the inside is also 2. So now they are able to be added together. So the way that I would do that is actually similar to what we did with adding and subtracting fractions, where the 5 and the 3 would get added together. Because what this is saying is that I have 5 square roots of 2. So like this is square root of 2 plus 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 square root of 2, right? 5 square roots of 2. And then this is telling me I have 3 of them. So all I'm doing is really just counting how many square roots of 2 I have. So 5 plus 3 gives me 8 square roots of 2. So square root of 50 plus square root of 18 equals 8 square root of 2. All right, let's look at another example with subtraction. So maybe I'm going to do the square root of 108 minus the square root of 48. So let's split that one up. Okay, so square root of 108, maybe we're not so sure what it splits into. So let's see if we divided it by 3. So the trick here that I know I can try 3, similar to the 9s, 1 plus 0 plus 8 equals 9, and 9 is divisible by 3, so that tells me that 108 is divisible by 3. So that's the trick to tell you that you're probably going to be able to divide by 3. So what is 108 divided by 3? 3 goes into 10 3 times, so that gives me 10 minus 9 is 1. The 8 drops down, and then 3 goes into 18 6 times. So 3 times 36 equals 108. And then 36 can split into 6 times 6. Now, technically, the 6s, they can go further, right? You can separate that into 2 and 3 and 2 and 3, but I know I'm looking for groups of 2 here. So actually, if I've already got a group of 2, I could just use that group of 2. Because what'll happen is I'll have a 2 on the outside, and I'll have a 3 on the outside, and 2 times 3 will give me that 6 on the outside anyway. So either way, if you'd like to find the ends, 2 times 3, you'll have a 6 on the outside. And then this 3 doesn't have a match, so it's going to stay on the inside there. All right, let's do 48. So another thing with that one, right, 4 and 8, if you add them together, it gives you 12. So this is also divisible by 3. So we could do the same thing here as we did with the other one, especially since our goal is to get a 3 as my radical, or my radicand. So 48 divided by 3. 3 goes into 4 one time. 4 minus 3 is 1, so you break down your 8, and then 3 goes into 8 6 times, so that gives me 16, which splits into 4 and 4. So again, this is the same thing where you could just stop here because you do have a pair of 4s, or you can find your 2 groups of 2 and have 2 times 2 on the outside, which is going to give you the 4 anyway. So either way, you could do that. Then this 3 that was here didn't have a match, so it stays on the inside, and now my indices and my radicands match, and I can do that subtraction. So that's equal to 6 minus 4, which is 2, square root of 3 for my final answer. 2 square root of 3. When multiplying radicals, the rule here that you want to follow is that the outsides need to multiply to the outsides, and the insides need to multiply to the insides, and they cannot cross through each other. Let's look at an example. Let's say we've got 2 cube root of 4 times 5 cube root of 7. Okay, so notice how, like we talked about with addition, the radicands don't match, but actually for multiplication, they don't need to. But the indices still do. So both of these being 3 means that we can do this multiplication. If this number was different than this one, then this would be as far as it could go. But they do match, so we can do this multiplication. So like I said, outsides have to multiply to outsides only, and insides have to multiply to insides only. So we have a 2 on the outside here, and a 5 on the outside here. So you will just do 2 times 5, and that will give you 10. And then now the insides multiply together. So the cube root, and then 4 times 7 gives me 28. So this is 10 cube root of 28. Now what you do want to be careful of here is just make sure that the number that's left on the inside of the radicand can't be simplified any further. In this case, it can't, because it'll split into 4 and 7. That'll give me 2 2s and 1 7, so there's no groups of 3 here. This one is done. 10 cube root of 28, so it's just 2 times 5 and 4 times 7. That's all that multiplication needs. Dividing radicals, it actually works very similarly to the multiplication. So let's look at that one. Let's say we've got 6 cube root of 16, and we're going to divide that by 4 cube root of 4. So what we need to do is we need to simplify the top just like it's one separate thing from the bottom. Okay, so if we look, we just ignore the bottom for now, just look at the top. If you were trying to simplify this fraction, okay, or just simplify this radical, sorry. So 6 cube root of 16. So 16, we want to check to see if there's anything that can break apart with. So let's do that factor tree with 16. I know that 16 is 4 times 4, and then 2 times 2, and 2 times 2, and I'm looking for groups of 3. So I have a group of 3 here. So that's going to give me a 2 on the outside. And then this 2 down here is all by itself, so it stays on the inside. This 6 right here is still out there. We don't want to forget about it. So it's still on the outside. It's just we've taken a group of 2's to put next to it. Okay, so 6 times 2, and then the cube root of 2. 6 times 2 would give me 12. So I'll have 12 cube root of 2 here. Okay, so now let's look at the denominator and see if we can simplify the denominator at all. In this case, the 4 would split into 2 times 2, which won't give us any groups of 3. So actually, the denominator here is as simple as it gets. So we can just move that across to our fraction here. So now we have a fully simplified top and a fully simplified bottom, and we're able to simplify or do the division now. So what's going to happen is, because it follows the same rule as the multiplication does, where you can only divide the outsides by the outsides and you can only divide the insides by the insides, you almost end up with these kind of 2 separate fractions that you need to use your fraction rules to simplify. Okay, so let's move that over here. So if I've got kind of these 2 columns of fractions, so I have this 12 over the 4 as one fraction, and then I have the cube root of 2 and the cube root of 4 as this other fraction, okay? So even though these are multiplying together, we do just want to treat them separately. So this 12 and this 4, when we simplify that, 12 is divisible by 4. So this 12, when you divide it by 4, 12 divided by 4 gives me 3. 4 divided by 4 gives me 1. Okay? Now let's look at this fraction here. The 2 and the 4 are both divisible by 2. So we can do that divided by 2 and that divided by 2. So the cube root of 2 divided by 2 is 1. And the cube root of 4 divided by 2 gives me 2. Okay, so now let's just look at simplifying as much as we can here. The cube root of 1 is 1. So 3 times 1 is just 3, and then 1 times the cube root of 2 is just the cube root of 2. So then 6 cube root of 16 divided by 4 cube root of 4 equals 3 cube root, or 3 over the cube root of 2. So that is the final answer there. Now we're going to look at simplifying radicals when there are variables involved. So we're going to just kind of put all these concepts into one thing, but we're going to break it down into each individual part. So let's say we've got the 4th root, and we're going to do w to the 8th power. X, give it some space. X is going to be raised to the 9th power. Y is going to be raised to the 3rd power, and then Z is going to be raised to the 7th power. Okay, so like I said, we're just going to just look at each thing individually. So w to the 8th power, if you remember, that's just w being multiplied to itself 8 times. So this is 1, 2, 3, 4, 5, 6, 7, and 8 with the w. Okay? So this shows us I've got 8 w's here, all being multiplied together. These are the factors of w to the 8th power. So we're basically kind of splitting it up, just like we did with the numbers, making like the factor tree. And then we're looking for groups of 4. So in this case, I've got a group of 4 here, and a group of 4 there. Okay, so let's take a minute on that just for a second. Let's look at now the x's. So now I've got 9 x's. So this is times x, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got 9 x's. And I'm still looking for groups of 4. So I've got a group of 4 here and a group of 4 here. So on this one, I've got 2 groups of 4 with 1 left over. Let's keep going. So now we're on the y's, and we just have 3 of those. So 1, 2, 3 there. So here, I'm looking for groups of 4, but do I have enough y's to make a group of 4? I do not. So I'm not going to be circling any groups of y's there. So let's move on to the z. So 7 of those. So 1, 2, 3, 4, 5, 6, 7. 7 of the z's, and I'm looking for groups of 4. So I've got a group of 4 here. So just 1 group of 4 and 3 left over. Okay, so this is the expanded 4 of that radical there. And this is telling me to look for groups of 4, so we did that. Now we're just going to put all of our groups of 4 on the outside, right? So here is my 2 groups of 4. So that's going to give myself some more room here for this one. That means that I can have a W squared on the outside, because this would be one W on the outside, this would be another W on the outside, and then the W times W would give me W squared. So that's going to come out. Now let's look at the X's. So here I've got 2 groups of 4 for the X's. So again, that's going to be X squared there, but then I have one X that's left over. So that X can be there, still left on the inside because it didn't have a match, so it stays in there. Now let's look at the Y's. The Y's didn't have any groups, so all 3 of these Y's are going to stay on the inside as Y cubed. Now we've got the Z's here. I only had one group of 4 with my Z, so just one Z goes to the outside. Here, I've got three Z's left without any group, so Z cubed stays on the inside. Okay, so all of the things that have moved to the outside with the groups and all the things that get left over, that's all done. So this is my final answer. So the W's, all of the W's go out because I'm looking for groups of 4 here. So this is telling me how many groups of 4 can I make with 8? 2 of them, with nothing left over. So nothing's inside. Now I'm looking, how many groups of 4 can I make with 9? I can make 2 groups of 4 with 1 left over, because 4 times 2 gives me 8, and then there's 1 left. Then how many groups of 4 can I make with 3? None, so all 3 just stay. And then how many groups of 4 can I make in 7? I can make 1 group with 7 with 3 left over. All right, so, but you don't always have to write all of this out. You can just look at the numbers you've got and think about how many groups are in each number and then what's left over. So on the outside here, this is going to tell me how many groups of whatever my index is. And then this is going to tell me what's left over after I make those groups. Okay, so if that's something you want to include with your notes, those little hints there, that might be a good idea. So let's look at another example. Let's say I've got the cube root of x to the 21 times y to the 29th power. Okay, so much bigger numbers here, so it might be kind of a pain to go in and write out all these x's and write out all these y's, but you can just use the thing we talked about with groups, right? So 21, I'm looking at how many groups of 3 can I make with 21? Well, 3 goes into 21 7 times. I can make 7 groups. So x to the 7th is going to be on the outside. Is there anything left over when I take away those 7 groups? Well, 7 times 3 gives me 21, so that takes away all of the x's. There's nothing left. Let's look at 29 now. So how many groups of 3 can I make in 29? Well, 3 times 9 equals 27, and then there would be 2 left over when I do that. So y to the 9th power, I can make 9 groups of 3 here, and then there's 2 left over, so y squared. So then this answer is x to the 7th, y to the 9th, cube root of y squared. So that is what you do when you're simplifying radicals that have variables. Okay, so remember, adding and subtracting radicals, you have to make sure that the indices are the same and the radicands are the same. But when we're putting variables in it, there is this extra step that we need to worry about. So if I've got the square root, let's say x square root of y, and I'm trying to add that to x square root of y. From here, I can do this addition, okay? So x plus x would be 2x, and then the square roots of y are going to stay the same, right? Because this is x square roots of y plus x square roots of y. So there's 2x square roots of y. All right, so inside the radicand stays the same, and you just add the variables together. That's going to give me 2x. If anything at all changes from this process, I will not be able to add them anymore. If I do x squared plus, or x squared square root of y plus x square root of y, this won't add together. This is as simple as this could be. If you are given this problem and asked to do the addition, this is as far as it goes. If you change the indices at all, if the indices don't match, you won't be able to do this addition. If you change the radicands to be different, so maybe this was a z instead of a y, you won't be able to do this addition. It won't go any further. So the variables on the outside have to match, the radicands on the inside have to match, and the indices have to match in order to get this addition to happen. So let's look at multiplication. I've got x to the 4th cube root of y squared, and I'm going to multiply that by x to the 5th, the cube root of y squared. Actually, we can even just make this a y. So, because it doesn't matter with multiplication if the radicands match. The only thing that needs to match is the indices. So now I'm gonna use the multiplication rule where I multiply the outsides together. So x to the 4th times x to the 5th. So that's here. And then the cube root of y squared times the cube root of y here. So now when I do this multiplication, I have x to the 4th times x to the 5th. That's going to give me x to the 9th, that you remember from your exponent rules, that you would just add the 4 and the 5 together. And then the cube root of y squared times y will be y cubed. So now I have x to the 9th cube root of y cubed, but this isn't done yet because actually I can still simplify this part here. If the number I got here wouldn't simplify any further, then this would be my final answer. But here I'm looking for groups of 3, and this tells me that I can have one group of 3. So x to the 9th is still there. And then because I can do one group of 3 there, the cube root of y cubed is y. So my final answer is x to the 9th y. So that's multiplication. Let's do another example with the concept of division. So let's say I've got x to the 7th, 4th root of y squared, and that's being divided by x cubed, 4th root of y cubed. Okay, so remember what we did before with division, where we basically end up making kind of 2 columns of fractions here. So I'm gonna have x to the 7th over x cubed, and I am going to have the 4th root of y squared and the 4th root of y cubed as 2 separate things, because the outsides have to divide separately from the insides. So if you remember from your exponent rules here, the 7 is the bigger number, so this is going to become a 1, and up here is going to be x to the 7th minus 3. And then here, the 3 is the one that's bigger. So now this is going to become a 1, and this is going to move. So that's going to become a 1. And then down here, we're going to have the 3 minus 2. So if we finish doing that simplification, we're going to have x to the 7 minus 3 is 4, and that's going to be on top of the 4th root y to the 1. 3 minus 2 gives me 1. So this is my final answer, x to the 4th over the 4th root of y. Okay, that is the basics of simplifying, adding and subtracting, and multiplying and dividing radicals. Hopefully you have taken some notes, and make sure you do the practice activities that go with this concept, and I look forward to seeing you in the next one. Bye!